we are going to continue with the course that is a structural design, and this is the second video that I want to share with you so that you can have the preliminary information pertaining to whatever we are supposed to do. And I'm going to have and share the notes on a screen. And in sharing the screen, we are going to be able to analyze effectively whatever we are supposed to do. So in this second video, I want us to discuss about or continue with the characteristic strength of materials. And remember, we just said that in the third topic, we are supposed to learn about the ultimate state design and also the comfortability limit state design. And we said that for any design to be accepted, it must have achieved some probability of acceptance. And it should guarantee that the structure is going to perform effectively or satisfactorily during its lifespan. And this is guaranteed by making sure that it is carrying the light load and that the excessive load is not deforming or it is not making our structure to fail. Then it should not deform excessively. That is, we have an allowable deformation. But if it deform excessively, it will not be of use, or it will be not be of substance to the occupant. Then it should be durable. So we discuss about the ultimate limit state design. We also discuss about feasibility limit state design. And today's lesson, in this video, I want us to discuss about something that is called characteristic strength of concrete. And when we are looking at the characteristic strength of the concrete, we are saying that the characteristic strength or grade of materials are as follows. One, we have the concrete. We said in the previous video that concrete is made up of cement, sand, and ballast. Then it is mixed with water. And if it is a reinforced concrete, there is some reinforcement material that are accompanying that concrete, and then the whole item is known as the compound or composite material. The characteristic strength of the concrete is given by FCU, and in this case, we are going always to be saying that FCU is the 28-day cube strength in Newton per millimeter squared. And we said that if, for example, it is 20, 25, and 30, that FCU 20, FCU 25, FCU 30, it is dependent on the way that concrete has been mixed. And therefore, FCU of 28, that is the 28-day cube strength, meaning that we are only taking the strength of concrete after 28 days. In these 28 days, there is curing that is taking place. So the 28th day of curing of that concrete is the one that is going to give us the light strength of that concrete. For example, 20, 25, and 30. So FCU is the characteristic strength of concrete. It can be 10, 15, 20, 25, 30, as we did so in the previous case. Then we have the reinforcement parts of the concrete. We know that the concrete, that is the reinforcement part of the reinforcement concrete. It can have Fy of 250 or Fy of 460, and we say that this is dependent on the way that reinforcement has been prepared. For example, hot rolled mild steel have Fy, the characteristic strength of the reinforcement of 250 Newton per millimeter square, while the hot yield strength, which is not lulled or cooled, have Fy of 460 Newton per millimeter squared. So we are going to see the characteristic strength of concrete. You divide by the partial factor of safety. That is the one that is going to give us these parameters for the ultimate limit state design. So we are going to see it at detail. This factor of safety is dependent on the that is the factor of safety that we need to take to account. Is that is they include something to do with the what? Something to do with uncertainties, or why do we have the factor of safety? One of them is because there is uncertainty that occurs with the strength when we are preparing the strength of that material. The second one is uncertainty, or we are using the factor of safety because of uncertainties in our calculations. Maybe the way we calculate is not, that is, there is some errors. So we are using those factor of safety to cater for those errors. Then at the same time, you are also using the factor of safety because of variation in member size and building. That is another reason as why we are using the factor of safety. There is something else that is called the characteristic load and the design load. We know that when we are doing the loading of the structure, we said that we have the life load and also the dead load. When we have the life load, that is the material that can be removed from that structure. But the dead load, in the other case, these are the materials that are making that structure. So we have the characteristic load and we have the uncharacteristic load. The characteristic load and the design load. The design load is the one that has the factor of safety, while the characteristic load does not have the factor of safety. So the characteristic or surface load are the actual loading that the structure is designed to carry. This is normally thought of the maximum load which will not be exceeded during the lifespan of that structure. And in most cases, in statistical terms, the characteristic load have 95% probability of not being exceeded. So that means that in any structure, we have the load which the building is designed to carry. And in this case, we are saying that the maximum load that building can carry should not be exceeded in any way, otherwise it is going to fail. So when we are looking at the characteristic load, we are looking at both the dead load and also the life load. In this case, the dead load is going to be given the abbreviation GK, as you can see from number 1. And this one, the dead load, we are saying that it is the self weight of the structure, including the finishes, the ceiling, the partitions, and the like. So the weight of the column, the slab, the footing, the foundation, the finishings, the ceiling, the partitions, these are the dead load of the structure. And we are saying that they are abbreviated by GK. That is the first characteristic load. Then from there, we have the imposed load. Imposed load includes the people who are occupying that building, including the furniture, including the water. Water itself is, when it is in a tank, water itself is occupying that tank. So water is the life load, but tank itself is the dead load. The weight of the tank is for the dead load. The weight of the water is for the life load. In short, imposed load or life load, these are the loads that can be removed from that structure. and they are given, they are abbreviated by QK. These are the imposed load. Then we have the design load. The design load, these are the characteristic load multiplied by the partial factor of safety. So when you have the GK, you multiply by a factor of safety, it becomes the design load. When you have the QK, you multiply by the factor of safety, it becomes the design load. So the factor of safety, we said that it takes care of, number one, the possible increase in the loading. Number two, the inaccuracy that occur with our calculation, all with the loading. And also the unforeseen distribution of the members, that the distribution of the stresses within the members, and also the importance of limit state design being considered. So in this case, we have the combination of the loading. That is, we can combine the dead load and the life load. For example, when water is in a tank, or when water is put in a tank, we have the water weight, that's the life load. We have the weight of the tank, that is the dead load. The combination of the two, it occurs in any case. And that is, when we have water in the tank, there is combination of the loading. And therefore, we can have the dead load and the life load being combined. In short, life load occupies the dead load, or it is there to that is, the dead load is there to cater for the life load. So the first combination, as you can see from this table, on the first column we have the load combination, on the second column we have the load type. In this load type section, we have the factors of safety. As you can see from, for example, the one that is named number one, we have the dead and the imposed load. In this case, if you want to get the factor of safety, in this case for the dead load, you can either use 1.4 or 1.0. The imposed of life load, you can either use 1.6 or 0. The R and the width, if they are there, you use 1.4 or you can use a dash. The second case, or the second combination, is whereby we have the dead load and the width. And you also have the other ends. So the life load, the dead load, in this case, you are going to use 1.4 and 1.0 or 1.0 as the factor of safety. You don't have the imposed load because you have not been given E number 2. But you have the width and the R. You are going to use 1.4 as the factor of safety. Then you have the dead load, width, and the imposed. In this case, if you have the combination of the three, you are going to use, in each case, the factor of safety is 1.2. That is how you get the factor of safety. Then from there, you can have, we are going to get the case scenarios, or we are going to have the case scenarios, whereby you have the dead load and the life load. All the loading, in this case, you can combine the two, the dead load and the imposed load. All spans are loaded with the maximum design load, that is 1.4 GK and 1.6 QK. And 1.4 and 1.6, we have just said that these are the factor of safety. Alternatively, the span are loaded with the maximum load, the load by combination of 1.4 and 1.6, and all other spannings with the maximum loading of 1.0. Getting that information from this diagram, you get from the left hand side and the right hand side, you have the maximum combination of the loading, which is 1.4 GK and 1.6 QK. while in between the two supports, you have 1.0 GK and 1.0 QK as the minimum loading that can occur. So 1.0 in that case, this is the factor of safety that can be applied in the minimum design load. But in the maximum, you have 1.4 GK and 1.6 QK. But when you have the loading in between the two supports, then there is interchange of 1.4 and 1.6 with 1.0, as you can see. Then from there, you can have the dead load GK and the life load WK, that is the width. If the dead load and the width load act in the same direction, as you can see, or their effect are additive, the loading combination is 1.4 GK plus 1.4 QK. That is the formula that you use to calculate the design load in case of the dead load and the width, the combination of the two. However, we are saying that if the effect are in the opposite direction, e.g. width lift, the critical load, then the combination is 1.0 GK minus 1.4 WK. That is 1.0 is the factor of safety that will cater for the dead load, and 1.4 WK, 1.4 will be the factor of safety for the weight. In the same note, you can have the combination of the dead load, the imposed load, and the weight. In that case, you have been given the formula that you're supposed to use, as you can see, which is 1.2 GK plus 1.2 QK plus 1.2 WK, as you can see from that formula. We are going to do it practically so that you can be able to understand fully. So, in the analysis of the structure, you can have I want us to introduce the way you are going to analyze the structure. In any structure, it must be rigid. The structure should be rigid. And when we are talking about the reinforcement concrete, it's a combination of the beam, the column, the slab, and the walling. And they are held together such that they act as one component, that is monolithic frame. But in each individual member, it must be able to accept or resist the loading that occurs in it or on it. So although they are acting as one member or a monolithic frame, each member is carrying its own weight or the weight that is imposed on it. And therefore, it must be able to resist the loading. So we are going to see how that we are supposed to apply the moment and the shearing coefficient in the calculation. And when we are doing this, there is a tabulation or a table of coefficients that are suitable for us to use in order for us to be able to calculate the weighting of the structure. So tabulated coefficients are suitable for use only with simple and regular structures such as equal span continuous beam carrying uniform load. Then we are going to have some manual calculations. In most cases, although it is tedious, we are going to have or we are need to have the manual calculations. But in most cases, when we are designing, we are using the computer methods, or we are using the computer for analysis. Then the analysis of simply supported load beam, we need to know that one span simply supported beam are statistically determinant. That is, we can be able to determine its force, the weight, and everything statistically. And the analysis of the bending moment and the shearing force is leadily performed manually. We can only perform the calculation of the bending moment, the shearing force, manually. For the ultimate limit states, we need only to consider the maximum loading, that is 1.4 GK plus 1.6 QK on the span. Methods of analysis, we can use the formula for manual. In this case, you have the simply supported beam, as you can see. It is carrying W kilonewton per meter, that is the uniform distributed load. We have VA and VB, which is the shearing force that are supporting that weight. And if you remember from structural mechanics 2, we said that the maximum loading, maximum moment is WL squared over 8 kilonewton per meter. That's the maximum loading. And then you have the VA is equals to VB. You say that, and it is given by WL. You divide by 2. Weight, you multiply by the length, you divide by 2 to give us the shearing. Then from there, you need to, after you have calculated the moment, you need to be able to draw the shearing diagram, the bending moment diagram, as we did in structural mechanics 1, and also the bending moment in diagram. That is what we did in structural mechanics 1 and structural mechanics 2. And I'm just going to give you a hint of what you're supposed to do. You calculate the loading, yes. You draw the first diagram, the loading diagram. Then on bottom of that, you draw the shear force diagram, and then you draw the bending moment diagram. That is just what we did in structural mechanics 1. So that is exactly what we are supposed to do. I'm going to stop there and then share another video, another screen, sorry. I'm going to share another screen with you guys so that we can be able to have effective analysis, so that you can have effective analysis. Let me share another screen. It is not the light one, but generally this is not a difficult course. We need to know how to go about it. We need to know how to be able to apply different yeah, I think I'm going to, this is a good point whereby I'm supposed to start doing some calculations, and I'm just going to introduce the calculations, and then from there we are going to have the actual design in a later point of time. So we are going to see that when we are designing, we have the design of a rectangular beam section. The design of a rectangular beam section, we are going to design a beam. And when we are designing the beam, we are going to apply the knowledge that we have just gotten, and then we are going to be able to come face to face and discuss in detail. So the design of a rectangular beam. This is exactly what we are going to do in the exam. This is exactly what you are going to be examining. So it is good to spend a lot of time in doing this one. And I propose that you are going to use maximum time in order for you to be able to understand fully whatever we are doing. So I'm going to start off with the beam. I will go to the column and I will go to the footing. So there is no point of worry for you. So we are designing to BS 8110, and I say that this is a British standard code of practice, but currently we are using the European code of practice in the field. But I want you to have the tables. I'm going to share with you some tables that you are going to use in we are going to use in our calculations, and we are going to get or grasp the information the way it is. So the design of rectangular beam section and the T-beam section to BS 8110 is the first thing that we are going to look at. And therefore, we are going to look at the type of the beam section. We are going to see that we have the rectangular beam section, and also we have the L. As you can see, we have the rectangular beam section, whereby the H is greater than that will be, as you can see from number A diagram. Then we are going to have the fridge, the B fridge, meaning that it is L beam section. And then you are going to have the B fringe, as you can see from number B and C, but number C is the one that is T beam section. So these are the three sections of the beam that we are going to consider. That is the type of the beam section. Then we are going to design for the tension reinforcement. We are going to design for the shear reinforcement, and we are going to design for the serviceability and also the reinforcement detail. So I'm going to just show you that these are some of the ways that we design. When we look at the beam section, as you can see, there is this section that is called the breadth. When we are designing, we must have the strength, the breadth, the height, and also the depth. There is a difference between an effective depth and also the depth. When we are looking at the effective depth, it is the distance between the two reinforcements. The center of the bottom reinforcement to the top of that beam. The breadth, as you can see, you have been given. Then the shear strip. The shear strip is the one that is joining the reinforcement bars. That is the top part of the bar. As you can see, these are the tension, for the tension, and the bottom part, they are for, that is the bottom part are for the tension and the top part are for the compression, sorry. Then they are joined by the shear strip stallops, the shear stallup, the links, they are the ones that are joining them. Then from that stallup, as you can see from to the top, you can see that there is a layer, that is the cover. Whatever is covering that stallup is the concrete cover. So at the top, as you can see, these are the compression reinforcements, while at the bottom, they are for the tension reinforcement. Then the same can be seen from this one, the cross section. At the top, you have the compression reinforcement bars. At the bottom, you have the tension reinforcement bars. The stallups, as you can see, they are joining the top and the bottom bars. Those are the stallup, as you can see. This is the beam, a horizontal beam section. So when we are designing of rectangular reinforcement concrete beam to BS 8110, or at 100, this is the procedure that you need to apply. That is, the first thing that you need to do is to determine the design life of that structure. What is the design life? What is the lifespan of that structure? The second case is to assess the action on the beam, to be as that one. Then you need to determine the combination of the loading, then determine the loading arrangements, then assess the durability, then you check for the requirement of fire resistance, then you determine the minimum cover so that you can cater for the durability, the fire, and also the board requirements. You can also analyze the structure to obtain the critical moments. Then you design for the reinforcement, you design for the shear. This is just you design for deflection, then spacing for the bars, and also you sketch the detail. This is exactly what we are going to do. This is exactly what we are going to do. So in the design for the effective span of the beam, you need to know that the effective span for the beam, you can have the effective span in terms of the depth or the breadth. So the effective span for a simply supported beam, it is the effective span of a simply supported beam may be taken as a smaller distance between the two centers of the support. So if I have a simply supported beam, the distance from the center of the first column or the first support to the center of the other support, the distance at the center of the two support is the one that is called the effective span of that beam. So the first thing that you need to know or to do when you are calculating the effective span is to be able to determine the effective span of that beam. Sorry, just a minute. I'm sorry. Just it was a minute. So when we are looking at the effective span of a simply supported beam, we are looking at the distance between the two support. We are going to see it, and I will make sure that I have a face-to-face class with you guys, so there is no point of worry. Then the second thing that we need to know when we are designing is to be able to size the beam. Sizing the beam, meaning that we are determining the breadth, the beam, which is the width of the beam section. We are determining the value of H, which is the overall depth of the beam section. We are determining the H, which is the width, or that is the effective depth of the beam section. And we are also determining the LE, which is the effective span. The effective span is the distance between the two supports, the center of the two supports. So in this case, we are going to size the beam, and when we are sizing the beam, the whole issue is to be able to calculate the H, the B, the D, and LE. This is a rectangular cross section. As you can see, there is a difference between D and H. The D is the overall depth, of that beam, while that is the H. The D is the effective length of the beam section, the effective depth, the distance from the center of the bottom reinforcement to the topmost part of that section, as you can see. When we are determining the value of B, which is the breadth, that is the breadth of the beam, the value of B, we are going to see that it should always be greater or equals to LE over that T. LE is the distance between the two supports, the center of the two supports. So we are going to know that if I have the value of LE, I can be able to calculate. I can be able to determine the value of the breadth. Then the value of D will be the value of 2 times B. So I just need to know what is the value of B. Then I multiply with 2 in order for me to get the value of B. Then from there, you can be able to get the value of H by adding D plus the cover, the concrete cover. You add it to the diameter divided by 2. Then we are also going to add something that is called tolerance in that case. B and H should be a multiple of 50. And generally, they start from 150 millimeters all the way to wherever. But it should be a multiple of 50. Then number C, we need to know how to compute the design loading. When we are calculating the design loading, we are calculating the characteristic load design, GK, and also the characteristic life loading, which is QK. And the characteristic loading, GK and QK,